In previous videos, we talked about the cornea torosity, the refractive index of the cornea, the anatomical structure of the cornea. Right now, we want to talk about cornea asphericity. So first, we need to talk about what is asphericity. So asphericity, most of the time, when we say some shape is aspheric, when we put aspheric means it's not spheric. So it means that the surface, we cannot put one sphere to define the whole surface. Like this shape, you can see this is a kind of aspheric lens, that the whole surface maybe here is a portion of a sphere, but the whole surface is not like a complete spherical shape. You can see this is a kind of lens that we call it aspheric lens. Those kind of lens are also aspheric. So the main difference between aspheric lens and spherical lens is that we don't have spherical aberrations because the surface is not spheric. We don't have that kind of aberration. But in order to make that kind of lens, we need to spend a lot of time and money because you cannot just put a spherical polisher and polish it like regular lens. So those are usually much more expensive than regular spherical lens. But you can minimize the spherical aberration, chromatic aberration, and even distortion into our optical system. But our eye is a kind of aspheric surface, so it's like a very expensive lens. So now let's talk about the mathematics of aspheric surface. This is the equation that we have for any kind of aspheric surface. So H2 is equivalent to x2 plus y2. Instead of just z2, we put a constant 1 plus q minus 2z are equal to 0. So just in your mind, if you put q equal to 0, it's going to be a spherical surface that is offset by r. So if you look at the math, you can say, yeah, it's a kind of completely spherical surface. But right now, we have a coefficient for z. And this coefficient, we call it surface asphericity, that we indicated by q. R is the radius of curvature, but for aspheric surface, the radius of curvature is not constant, as I mentioned before. But at the vertex, at the center, we have a radius of curvature. That radius of curvature is R. So in order to actually define a aspheric surface, we only need two parameters. One is Q, which we call it surface asphericity, and R, which is the radius of curvature at the vertex. So in this equation, this R is the distance from the axis, and Z is the distance from here to there. And then we call it aspheric surface. Now, when Q is negative, we have hyperboloid. When Q is exactly equal to 1, paraboloid. When Q is between -1 to 0, this surface we call it ellipsoid. When Q is equal to 0, this is a perfect sphere. When Q is bigger than 0, we call it ellipsoid with the major axis in xy plane. So now let's look at those numbers. This is a simulation for Q is equal to 0 at the center. Q is equal to 1, 2. So now let's look at another graph. As I mentioned before, it's like when Q is equal to 0, it's complete a sphere that is offset by R from the center. So this is a sphere. When Q is more than 0, it's gonna get smaller and smaller. When Q is between -1 to 0, again, it's ellipsoid but bigger. When Q is equal to -1, it's paraboloid. And when Q is less than -1, we call it hyperboloid. And for our eye, Q is in this range. So Q is between -1 and 0. Now let's look at some data actually for anterior and posterior surface. We should be very careful. Both surface of our eye has some kind of asphericity. in the anterior surface and posterior surface. So you can see, for example, Mandel and Helen in 1971, they did it for 8 eyes actually, and the anterior surface Q is negative 0.23, and for posterior they don't have any data. As you remember, in one of my previous videos I explained that we usually don't have that much of data for posterior surface, because anterior surface you can directly measure it, but for posterior surface no, it's a little bit harder. And in 1985, negative 0.28 plus or minus 0.13, if you have a big standard deviation, and the number is changing also. So you can see we have a big range of data and statistical standard deviation. Some of the data we have some data for posterior, and for posterior is the same. We have a big standard deviation and even the variation and the mean. So it looks like we don't have a good way of measuring it, or even if we can measure it, it's changed between people a lot. So we cannot say we have a constant value, but we have a mean value, which is unweighted average of all the data. For anterior surface, we usually use negative 0.21, and for posterior surface, we usually use negative 0.45. So here are some references that I use for this video. Thank you.